Hello, everyone. We are back again with our second part of chapter 16. Today we are going to talk about the relationships between acids and bases. So if you haven't watched 16-1, that is the first installment that talks about the different properties of acids and bases. So please, if you haven't watched that or read that portion of the textbook and feel like you thoroughly understand it, please do that before you watch this video. So last time we talked about how weak acids and weak bases form equilibria with water. And so to start off, I want to give you some definitions. So I'm going to use these generic forms of weak acids and weak bases, and we're going to be real creative where a weak acid is HA and a weak base is B. So if HA is our acid, an acid always reacts with a base, and it turns out that when this is in equilibrium with water, water is acting with our base. And remember that last time we talked about how bases have lone pairs? Well, if you remember from Lewis structures last semester, water, this oxygen, has actually two lone pairs. And so this lone pair on the oxygen can act as the base, taking the proton from the acid and creating H3O plus, the hydronium ion, and leaving A minus behind. Now, we give the name conjugate acid and conjugate base to these products. So notice how a conjugate acid is really still an acid. It still has a plus sign. And so we know that from last time that acids are cations, or actually I should say cations are acids. And we just tack on the term conjugate to indicate that this is the acid that was created when the base gained a proton. And so likewise, A minus is our conjugate base because anions behave like bases. And this is the conjugate. It's the product that formed when the acid lost its proton. And likewise, the base has the same idea. Our base B reacts with water, and this time our base, I'm going to give it lone pairs. Our base takes the proton, leaving behind a conjugate acid, and notice it's got to be an acid. It's got a plus charge. And it's got to have a plus charge because it's giving its electrons to take that H plus from that acid. And so that plus charge has to go somewhere. And this is the conjugate because this is the acid that formed from the base reacting with the acid. And likewise, the hydroxide is the conjugate base, minus signs, and bases correlate. And this is the conjugate because it is what formed when the water, in this case, which was acting as the acid, when the water lost its proton. So, what about water? I just showed you an example where water acted as both the acid and the base. And so here's more. So in this first example, the water is acting as a base. It's using its lone pairs to take a proton, and it's turning into a conjugate acid. So this is a base, and it's creating a conjugate acid as the hydronium ion. In the second reaction, water is acting as an acid. I'm going to change colors for you guys. Water is acting as the acid. So the base, in this case the ammonia, it takes takes a proton, and so remember that acids donate protons, and another way of donation is actually having it taken from you in the term of chemical reactions. So the ammonia takes this proton from the water, and that water turns into hydroxide. And so in this case, our hydroxide is our conjugate base, and our water is our acid. Species that can behave as both acids and bases are known as amphiprotic or amphoteric species. So amphiprotic or amphoteric species are both acids and bases. So when we get a species that is amphiprotic, we have to treat it as both an acid and a base. And that's going to affect our calculations down the road. And we'll get there later in this chapter. So, as we just discussed, water is amphiprotic. So to see this better, I like to write water as HOH, because this lets me see how the equilibrium exists when that water can break up into its ions, its H plus and its OH minus. And if we want to be real specific, we can write in that these are aqueous. Now, this is an equilibrium reaction happening here. Turns out that water is both a weak acid and a weak base. This equilibrium reaction of water is described by the Kw and is given as the definition of the products divided by the reactants, just like all Ks. But remember that our water is a liquid, and liquids do not appear in our K expression. So Kw becomes the concentration at equilibrium of H plus times the concentration at equilibrium of OH minus. It turns out that when water is in solution, that these equilibrium concentrations are known, and each one of them are 1 times 10 to the minus 7 molar. And so when we calculate that out, we get a Kw, that this is a defined value of Kw is equal to 1 times 10 to the minus 14. Okay, so some more definitions and relations that we're going to start using to be able to describe these solutions that are acidic and basic. One of these is pH. pH, these little p's, this little p, it just means to take the negative log of anything. And so we have lots of different p's that happen whenever we talk about acids and bases, because it turns out that the log scale makes a lot more sense for what we're working with. And so one of these is pH, and pH is defined as negative log, and these logs are always base 10. It's negative log of the concentration of the H3O plus at equilibrium. And likewise, we can describe a POH, which is minus log base 10 of the hydroxide concentration in a solution at equilibrium. Sometimes it's also convenient to talk about a pKa or a pKb. And again, these are minus log. They are both base 10 of the Ka or Kb. And so really, in this form, I could say I want to take P of dogs, and that means that I would take minus log base 10 of my number of dogs. So I can take P of anything. And so just remember that this little lowercase p isn't special. It just changes the scale of our numbers into things that are easier to read. Okay, so some more definitions and relations. We talked about this one just a little bit ago, that kW is equal to 1 times 10 to the minus 4. So what I'm working here, this is what we call a derivation. So I'm starting with relationships that I know, and I'm trying to figure out a new relationship based upon some algebraic manipulation. That's all a derivation means. So if I take this expression that I know, my concentration of my H3O plus times my concentration of my hydroxide is equal to 1 times 10 to the minus 4. I can take the log of both sides, log base 10 of both sides, which looks like so. And if I separate that out, now when the argument for a log is multiplied together, the algebra tells us that we can take the log of each of the things and add them together. So that's what I did here. I broke this apart and got rid of this complicated argument to break it up into two smaller arguments. And when the arguments are multiplied together and the log is taken of them, we add those. And so I've got the log base 10 of H3O plus the log base 10 of the hydroxide. And then if I take log base 10 of 1 times 10 to the minus 14, I get negative 14. So if I rearrange this and I move my negative sign around, so to go from here to here, I've just moved the negative sign by multiplying both sides by negative 1. And what I get is that the negative log base 10 of the H3O plus concentration minus log base 10 of the hydroxide concentration equals 14. Now, this term is also known as pH. And this term, including the minus sign, is also equal to the pOH. And so I can simplify this down to be that the pH plus the pOH is equal to 14. Okay, so some more definitions and relations. Let's just make sure that we remember these. So we talked in our first session about how the Ka and the Kb are defined. Now, notice I chose my Ka and my Kb very specifically here. In the first reaction, I have the generic acid Ha forming the conjugate base A minus. So this is my acid, and this is my conjugate base. In the second reaction, I have A minus as my base, forming the conjugate acid, Ha. If I can write, there we go. So with this, I have two definitions. One is the definition of the Ka, the other is the definition of the Kb. If I multiply the Ka and the Kb together, notice I just plugged in the two relationships. Notice how the A minus and the Ha cancel out. And so the Ka times the Kb becomes equal to the concentration of H3O plus times the concentration of OH minus, which is equal to the Kw. This is only true if we are discussing acid and conjugate base or vice versa. So, what do I mean? Notice how, in order for this to be true, this cancellation had to happen, which means that Ka and Kb have to be describing sort of the reverse reaction, where the conjugate base for one reaction is the same thing as the base for the other reaction. Okay, so that's all I have for definitions and relationships for this session. Stay tuned, and I will cover the next section of chapter 16 in the next video. Again, I have lots of office hours. Please reach out and talk to me if you have any questions. Thank you.